I will talk about matter in the universe and the forms of matter and how to calculate its properties. And as the title says, I will concentrate on 3 different forms of matter, which is collisionless, less collisionless, and collisional matter. And what I mean by that, I will describe in the talk. And here's the list of collaborators I have been working with. So I will start with the collisionless matter in the universe, and by that I mean the significant contribution of dark matter. So the current standard paradigm of LCDM is that dark matter is a key ingredient in structure formation, and this is what you all know. But the problem is that there is still no definite detection of dark matter, except for things like the gamma signal, which are not confirmed. So the key problem of the dark matter idea is essentially to detect dark matter, which was not done so far. And what I want to talk now, in the first part of my talk about, I want to talk about the properties of dark matter on very small scales, which are relevant for both direct and indirect detection experiments. And I will mainly present results based on embodied simulations, which is probably the best way to study the nonlinear machine of structure formation. So to start this, I want to first point out that we know today by very high resolution simulations of individual dark matter halos, like the Aquarius halos that we published finally, or the IKEA project and other high resolution simulations. We know that the phase space of dark matter halos is pretty rich. So there are gravitationally bound structures like subhalos, and there are tidal streams, which is shown here in these plots. So these are plots from one of the Aquarius halos that will be kind of materials. You have these subhalos here, and they have tidal material which gets tidally absorbed away from them, which builds some debris, and this is all over the place in the phase space of the halos. Now, obviously, this will all kind of affect the detection experiments, both direct and indirect, because subhalos, for example, as overdensities in the main halo will have strong annihilation signal, because the annihilation signal of the two-body process will be density squared. The streams, on the other hand, can have, although this is much of a debate, can have some impact on direct detection experiments. So they can, for example, be important for the ambient annihilation that you can observe. And so this is already an important structure in the halo that you have to take into account if you want to understand any outcome of the detection. Now, but what I want to talk about is going to smaller scales. So obviously the detectors that you have are very small compared to all these scales that you plot in the simulation, and what you really want to understand is the very fine grained distribution of dark matter. So you have the Earth in the halo somewhere, and you have a detector on Earth, and you want really to know what the fine grained distribution of the dark matter looks like to make that predictions for the signals. Now it's important that dark matter is collisionless, and we assume typically that the largest fraction of dark matter, if not all, is composed of a cold particle, which the leading candidate is the neutrino, which has a velocity dispersion in unclustered region of the universe today of 3 centimeters per second. If you have an axion, then it's even only 2 nanometers per second today. So these particles are extremely cold, and they are collisionless. So this means they completely follow the Blazov equation or Boltzmann equation. It's just the Boltzmann equation without any collisional terms. And that implies that they have a very peculiar or very special way how they evolve in phase space. So if you have a 2-dimensional phase space, just as a cartoon, this is position here and this is velocity, then dark matter will only occupy this black line here, which is in this case just a small hypersurface in this 2-dimensional phase space. Now, if you are at that position here, for example, you would measure exactly 1 velocity. If you are at that position here, you would measure 3 velocities. And the formation of halos and nonlinearities is exactly this process. It's a folding of the phase space T. So in our halo, essentially, we would have a situation like that with a strong wind-up, and then the question is how many of these streams do we effectively have at the position of the Earth? Because you can imagine if you have a dark matter detector here on Earth that will measure the energy distribution of the particles, then depending on the number of streams, you will get different signals. This number of streams in principle will be very low. Then it would be interesting from the detection point of view, because the signal would be very discrete, but it can also be, since we don't know exactly, be very high. And then you would get kind of a smooth cluster distribution. So that is one question, how many streams at the solar position do we have? Another question is that if you cross the one-stream region with a three-stream region here, and you assume you have a perfectly cold matter particle, so with zero velocity dispersion, then you can calculate the density here, and that density is then infinite. Of course, physically it's not infinite because it's cut off by the velocity dispersion that you have, but it's still pretty high, and that means that the annihilation radiation at these points will be very high, depending on how high the density is exactly. And these are so-called caustics, which could give a strong annihilation boost to the annihilation radiation, which is typically not taken into account. So you have two effects in this finite case. You have the streams, which affect direct detection experiments, and you have caustics, which typically mainly would affect indirect detection experiments. And what I want to talk now in the next few minutes about is what we expect for lambda CDM, or how this looks like. I mean, this is just a cartoon, so the question is how it looks in a lambda CDM calculation. Just to give you an idea that things like that were already calculated back in the 80s by Vogelsberger and also by Virginia and other people, where they came up with these very simplified one-dimensional self-similar models to explain halo formation. So this is just again a phase-space diagram of a halo that formed in these one-dimensional models. You have radial distance here, radial velocity here. And again, we get this phase-space pattern, and again, at these points here, you have the caustics where the density is very high, and here you have the discrete number of streams. Now, if you translate this in a radial density profile, which is shown here, then you get a mean density profile that follows something close to -2 in the tau down here. And on top of that, you have these spikes, and these spikes just correspond to the caustics. Now you can imagine that they will influence here the annihilation signal because you have this high density here. But this is just a one-dimensional calculation, which is very simple to do analytically, but which has probably not so much to do with reality. Now, to really study this in the full lambda CDM context, you have to do some kind of N-body simulations, and it's possible to resolve all these effects in N-body simulations if you just add a few more equations for the N-body integrator. So you can resolve, for example, the annihilation radiation of caustics, and you can calculate the stream densities, and yeah, you can essentially get all of this information out of the simulation. And I just want to point out two things. For example, the maximum cost density, if you calculate this analytically, which goes then into these N-body integrators, you can show that the maximum density scales like 1 over the velocity dispersion square root of it. So that just shows you the colder the particle gets, the higher the density, which means in the limit of perfectly cold material, you would just get infinite density, as I mentioned before. Now for the annihilation radiation, this is the expression for the annihilation radiation. That goes logarithmically with 1 over the velocity dispersion. So there's a beta dependence here, which is quite good because all predictions that I make now on the next slides will assume certain velocity dispersion, but this is only logarithmically dependent on the dispersion itself, so that's not strong dependency.
So what's the dimension of the caustics in a three-dimensional triac scale hole?
You mean the size or the
dimensionality? Are they still surfaces?
No, they are more what Craig Hogan called pancakes. I mean, these things are a lot more complicated. The spheres are only there if you have perfectly symmetry.
Well, I'm just interested in they go up, but they're still surfaces.
Yeah, mainly they are mainly surfaces. Yeah. Okay, so now you can calculate all this. Now you can put it in an N-body calculation, and that is just an example again of doing the same steps in the columns that I showed before in the analytic calculation. Now in an N-body calculation, where I showed here the outcome in annihilation radiation. So you see these rings here. These are essentially projections of the caustic surfaces in 2D, and the smooth signal behind is just a smooth annihilation signal. So you can see that due to the high density in that system, they really stand out and contribute to the annihilation signal here. And here I show again, this is a two-dimensional phase-space diagram where radial position here, radial velocity here. And the colors here are chosen according to when a particle passes through caustic. So there's always a caustic color change when there's a caustic current. You can see it's at these points. And each of these caustics corresponds then to one of these rings. So that's just confirming that the method kind of works. Now the The question is what happens if you do this in full lambda CDM. So for that, we took one of the various halos and ran them again with these additions to the code. And this is again phase-based diagrams. And now the color shows again how often particles pass through caustics. And you can see now here all these substructure which just pops out in the phase-based diagram. And you can also zoom in on the substructure and you can see how the details around the substructures look like. And you can remove also all the substructure and then you can see the stream-like structures. So these are essentially tidal streams, which is tidally disrupted material from the subcable stream. So that's just to give you an impression of how this looks like in a full LCDM halo, which is very different, of course, from these one-dimensional conditions. Now, more quantitatively, you can now ask what is the typical number of caustics that a particle has passed at a given radius, and you can express the radius as usually R200, units of R200. And then you can, this solid line here is now the medium profile of the caustic counts, and this increases towards the center, which is not surprising because the particles are just dynamically open in the center, and the dynamic time scale is shorter in the center. And the spread here is just showing different quartiles of the distribution, so you can see this is a pretty broad distribution. I also want to point out that these different colors here, at least in that plot, they show different resolution of the simulation, so this is all pretty well conversion actually. So this is a pretty stable result. So this plot shows essentially the same information just in different ways. So these are histograms of caustic counts where the different colors now correspond to different radial cuts that we make in the halo shells. So the red is the innermost particles. You can see this pretty broad contribution here to also pretty large caustic counts, which is again the center is probing these higher caustic counts, whereas if you go into the outer part between 80 and 260 kilopascal, you get this brown distribution, which is peaked more towards small caustic count, which all makes sense. Now you can also look at the cosmic web in the vicinity of the halo. So this is just a 1 megaparsec box, slightly more than 1 megaparsec box centered on the halo at redshift 0, and we filter now all the particles according to the number of caustics that they have passed. So here the particles that have passed no caustics, they are still in this pretty smooth distribution, so broadly linear. And then you have one caustic which starts to trace the complementary structure, the same for 2. And the higher you go in caustic count, the more you trace the centers of subhalos and halos essentially. So you can nicely compose the cosmic web. Now from a detection point of view, the first important question to ask is what is now the number of streams that we expect at the solar group? Yeah.
So is that a slice or a projection?
That's essentially, if I remember correctly, a projection of 1 megaparsec thickness. So it's just 1 cube of 1 megaparsec cycling.
So these things are projecting on the tomorrow. So here, yeah.
Yes, these are, yeah.
So they're filamentary?
Yeah, they're filamentary.
They're filamentary.
Yeah.
So then why do you say they're sheets? Why do you say they're surfaces?
Well, these are not, well, these are essentially, so the caustics themselves. So let me so if the particles go to a filament, then they have their first turning point. That is what happens here. Now, at the turning point, if you would calculate in detail the density structure there of the caustic, if it goes exactly to the caustic, then it's still a two-dimensional sheet-like structure. But the point is that all these caustics taken together, they all cluster around the filaments. The filaments are just 3D structures. Okay, now from a detection point of view, as I said, it's important to know the typical stream density and the number of streams that you have in such a halo, and this is shown in these two plots. So if we focus first on that plot, and the important lines are these lines here, these dashed lines. So different colors are again different numerical resolutions, and the number here, and of these lines show the typical number of streams that you expect at different radius. So the solar radius would be somewhere here. So you would expect of the order of 10 to the 6 or 10 to the 7 streams at that position. So from the one-dimensional calculation that I showed before, you would expect a typical number of 100 streams. Now this is significantly larger. So why is that a lot larger? Well, because the system is here three-dimensional, so this means the phase space is six-dimensional, and can show analytically that the stream density decays a lot faster in such a potential than in a one-dimensional potential. And on top of that, of course, there's a lot more perturbation in the one-to-scale power spectrum than in a single perturbation interaction. That's for this subsymbol models that I mentioned before. So there's a huge number of streams, which means for most detectors, like most neutralino or wind detectors, that would not make any difference in your detection signal compared to the smooth assumption. Now, there's one exception where it will make a difference, is if you have an axion as dark matter particle, then the axion detection principle is different from the wind detection experiment. So the axion can be detected by conversion to microwaves in the magnetic field, and that is because the axion Lagrangian has a coupling term to the EMP field. So, and these detectors have extremely good energy resolution. So the energy resolution is indeed so good that the most massive of these streams at the solar position would essentially make a signal to these detectors. So in the possible event that dark matter particle is an axion, then there is a chance that we will see some of these fine-grained streams in these axion detectors. But again, for the majority of the experiments, which are wind experiments, this does not play any role. And the main reason is that just the density of these streams is just too low, and then you get a large number and it doesn't play any role in detection. Now the second question is, how important is this for the annihilation radiation? So for the annihilation radiation, it's mainly the caustics that are important. And this is shown in that plot now, the important quantity. So this quantity here is just the annihilation radiation due to caustics divided by the smooth annihilation that you would get without caustics. So if that number would be very large, then there would be a significant contribution to the caustic. If it's very small, it's essentially negligible. Now the converged, or kind of converged result is the blue result here. You can see that at the solar position, you get a pretty small contribution, but even around real rays, you only get about 10% contribution. So it's not a huge factor that you miss in that calculation in terms of caustic annihilation. So that means if you just run a standard Radii simulation and calculate your smooth profiles and calculate the annihilation radiation, you do not miss a large fraction due to these fine-grained contributions. Now the reason, again, why this is such a small contribution is that the density of individual caustics is just pretty low, and that is shown in that plot. So the green here is the mean halo profile, and the red is the typical caustic density expected at the radius. Now you can see that there's crossing points slightly within R200, and at that point, the sun is approximately, there's already a huge difference between these densities. So obviously then these caustics cannot give a strong annihilation signal compared to the average density there. And you should compare this plot to the plot that I showed at the beginning when I discussed this one-dimensional model where you saw all these spikes on top of it. So this is now a very different situation. And again, the main reason for this is the additional power in the LCDM spectrum and the different dynamical situation with the high dimensionality of the system. So this means also that caustics do not play a role. So it seems that both streams are unimportant for detection experiments, except for caustic or for axions, and that caustics do not give a strong rise to annihilation radiation.
Excuse me.
Yeah.
You mentioned that this logarithmic dependence on the velocity dispersion of the.
Yes.
Is that in here somehow? Or
yes, so this is done for a certain particle where you have velocity dispersion of, if I remember correctly, 0.03 centimeters per second today. So this is in these results. Now, I have another plot at the end of the talk where if you change the velocity dispersion by 14 orders of magnitude, so you change the results only by a factor of a few. So that this is not, yeah, this still depends on the velocity dispersion, but very, very weak dependency. Now, all what I said so far is assuming a standard dark matter particle, certain velocity dispersion, and certain mass and so on. Now, there were around 2008, there were coming out these Fermi results, where Fermi saw this positron excess in the cosmic ray spectrum. And the problem with this excess was that if you want to explain it with dark matter annihilation, you have to invoke a certain boost factor to get the annihilation rate right. That is coming out of these calculations compared to the result. Now people have thought how to boost the result, so there's one possibility that it's substructure, but then it must be local substructure, and we have a pretty good handle on local substructure. There's not much of a boost to be expected. Now I just showed you that also caustics do not boost much around the sun. So what people then thought of was some particle physics mechanism, which is in that case the Sommerfeld mechanism, which would just, so to speak, for very cold particles or particles with very low local velocity dispersion, give an enhancement of the cross-section. So usually the cross-section is pretty well constrained by the relative abundance, but if you have such a model, then you can, for halo particles, you can essentially boost the cross-section by a factor of by 2 orders of magnitude typically, and then you can make these, you can explain these phenomena because essentially you have such a mechanism at work. Now I want to point out, if you have this mechanism at work, also the situation of the fine-grained contribution changes significantly. Because what I said before was that the caustics may need to be annihilation. Now in a system where you have Sommerfeld enhancement, particles with a low velocity dispersion get typically larger, get a larger cross-section and will also produce more annihilation. Now if you go to fine-grained properties, then the caustics, which have a very high density, must have automatically also a very high velocity dispersion, simply to preserve phase space density, so by the Vogelsberger theory. So this means they get a penalty for this high velocity dispersion, and their annihilation radiation will be not as high as the annihilation radiation in cold regions of the fine-grained phase space. And the cold regions in the fine-grained phase space are essentially extremes, because they have very low densities, as I mentioned before, so their velocity dispersion must also be very low. Now if you look at these plots, this is a plot where you should only focus on the solid line. So the red solid line is the kind of differential annihilation radiation for halo, and the blue is the contribution to the fine-grained phase space. And that is along the lines what I mentioned before, so it's always kind of subcoordinate, especially in the inner particles. Now you turn on this new particle physics and you completely invert the situation, so now you have a lot more annihilation radiation in the fine-grained contribution, and the smooth field is essentially subcoordinate. So if you would, in such a model, if you make an unbiased simulation, you calculate the annihilation radiation, it will be off by a significant factor because you typically do not take into account this kind of contribution. So that's just to point out that in such a particle physics model, the situation changes a bit, and the fine-grained properties really become then very important. Okay, so this leads me to the second part of the talk, where I want to talk about gas collision matter. And by that I mean self-interacting dark matter. So self-interacting dark matter was already very popular about 10 years ago, when Stein and Sparger proposed it. So now why is that coming back again? Well, it's mainly coming back for 2 reasons. So the first reason is that the Sommerfeld models that I was just talking about, they automatically also include some Ricardo coupling between the dark matter particles, so there's automatically some self-interaction in these models. And the second reason is that there were recently various problems with the Milky Way satellites that were mainly pointed out by micro intelligence based on body simulations. So this problem so this is just a plot of circular velocities. I'm sorry that this is cut off here. For some of the dwarfs in one of the Aquarius scales. And these are data points which are taken from 9 observed dwarfs in the Milky Way. And now the point is that these, if we only had in the simulation these dotted curves, then everything would be fine. So there's some, they go through these data points, so this is kind of okay. But in all the halos of the Aquarius and also of the VLRK simulations, we also have these massive dwarfs or subhalos which have least velocity curves. So they are a lot denser, essentially, than what is allowed from the observations. So there's this problem that essentially the most massive dwarfs in the simulations are too dense compared to what we have in the observations. So now this is a kind of a massive dwarf problem because these systems have Emax, as you can see, of 40-50 meters per second, so they are pretty massive systems. So you cannot do much probably with baryonic feedback, although this is kind of a debate. And so it's the question, how can you now solve this problem, which is probably harder to solve than the missing satellite problem, where you have more freedom in terms of practices. Now, with self-induction dark matter, and that was already known 10 years ago, you can produce pores in these systems, and the pore is exactly what you would need to essentially get the density down in the center of these systems. Now the problem with attempts 10 years ago was that there was first of all no real particle physics motivation for the cross-section, and secondly, typically the studies assumed either constant cross-section or fixed polar cross-section. Now these new particle physics models, which were mainly invented to explain the Cornell results, they have a very different cross-section behavior, which is shown here, which was worked out by various people. And then if you plot it, then it looks like that. So it has some peak, and then it has a strong decline here to the cluster scale, and it's kind of a bit flatter towards the smaller scales. And so if you look at the allowed regions for the cross-section and for this peak velocity, then there's, based on all these astrophysical constraints, there's some parameter space left where you could essentially turn this on, this particle physics, and get self-induction dark matter without violating any of the constraints which we currently have, especially not violating the cluster elliptic. So the question is, can you now, with such a model, get better agreement in these systems? So this is what I was working on recently with Gaseous, and so this is all very preliminary. So we just started the simulations a few weeks ago. So that's just these are just simple test calculations where we did isolated halos. So these are just Quanquist halos, where you can see here different halo masses, and I show you the scatter rate per particle and per giga year. And so the solid lines are here the constant cross sections, and the dashed lines are the systems with velocity dependent cross section. These are just the analytic prediction. So these are the embodied calculations where the colors are the embodied result and the dashed are the analytic result. So this is just to show you that this model works. Now the interesting part is not doing this these isolated test halos, but to full LCDM halos again. And again, we took one of the Aquarius halos, and we explored 4 different scenarios here. So the first, which I call reference point 0, it's just the standard number LCDM calculation of collisionless particle. So the same as the calculation that essentially did. So this is shown in black here. And the second one is reference point 1, which is similar to the models that were explored 10 years ago, although the cross-section is a bit large, of course. But this is just a constant cross-section, and you see you form that this is shown in blue here, you form this huge core, which is, of course, completely ruled out by many observations, and is completely violating the cluster elliptic measurements and so on. The interesting points are reference point 2 and 3, which have a certain cross-section at the maximum and a certain velocity where the cross-section peaks. And both of these points are fully consistent with any astrophysical constraint and are also allowed by particle physics from these models. Now in these systems you don't form a huge core, I mean you still form a little core, but you don't get this complete mess of the density growth at large rate. Now that's for the main halo profile, so this is of course not what we are interested in. So what we are mainly interested in are the subhalo properties. And this is the first thing you can look at is just making a subhalo mass function. So this is just the mass of the subhalos, and here I show the mass function of the simulations divided by some best fit mass function of the LCDM case. And the first thing you notice is that the blue is pretty much up here, which is again this constant cross-section case, which is anyway ruled out. The interesting point is that the red and the green kind of agree with the black, which tells you that these models do not do much harm to the subhalo mass function. So the point is I do not want to change the subhalo mass function, I just want to change the cores of these, or the settings of these systems. And that shows you already that the mass function is at least kind of preserved in these systems. Now, the important point is to look at the circular velocity curves, and this is now a circular velocity curve of the LCDM case. Now, those of you who remember the curves that I showed of Mike's paper might recognize that this looks very different, because suddenly all the curves go through data points. So the reason for that is that this is just a very low resolution simulation where the softening is very large, and these curves are also not correct. So this is, again, very preliminary. But you can compare this now with the self-conducting calculation, which has the same property for softening and so on. But you can already see that you push the curves in the right direction. Now what would happen if, the simulation with high resolution are currently running, if you go to higher resolution, then these curves will go somewhat to probably 10 to 15 meters per second, because we just have to have double profiles. Now they are already in kind of the chord regime, so I would think, although I cannot be 100% sure, that they still change a bit, but not so much. So this difference will probably get larger if we have the proper numerical resolution, which I unfortunately cannot show to you. So there's this possibility that self-conducting dark matter can kind of at least make the tension between the observation and the simulation a bit smaller. I'm not sure whether it can really solve it, but it can at least make it smaller. Another possibility is, of course, that you do warm dark matter, which color strength and some people enjoy that. You can also do that. Then you get also a better agreement here, but then typically you also change significantly the abundance of the subgroups, which is not bad, but which is just also an additional thing. And on top of that, you have typically these warm dark matter problems that the parameter space for warm dark matter is pretty small. Okay, so that was for less collisionless dark matter. So now I come to the fully collisional case. So going back to those. Yeah.
Is there any velocity dispersion as a function of radius information before? It was flat, or this would indicate that it should be increasing?
You mean observation? Yeah. I don't know. These are based essentially on half-light radius measurement and calculating the dynamic mass within these. So I'm not, I don't know which information power we need for this system.
These are all these Milky Way, the big low mass.
These ones?
Yeah.
No, these are the more massive ones. These are those ones which are really a Vmax 4 kilo. So these are not the smaller ones. Okay, so in the last probably 10-15 minutes I want to talk a bit about collisional matter. So why do I want to talk about that? Well, so all the other results that I showed so far were based on pure and body calculations, and obviously if you want to make proper connection to the visible universe, you also want to model the variance correctly, which is a collisional component. And so that's a different problem now. So where we solve in embodied calculations the Blasov equation with the Monte Carlo approach, because you cannot solve the partial differential equation directly. For hydrodynamics, you can essentially solve the partial differential equation exactly on the Euler equation, which is just mass momentum and energy conservation. And I guess all of you are familiar how this in general works. So you model the IGM as ideal with gas and couple it to self-property of matter and energy, and then you try to come up with a universe which has the correct properties of some variance. Now, although this sounds pretty simple, it became already clear many years ago that this is apparently not so simple, because if you do the most simple calculation by just doing non-radiative hydrodynamics, so you just take a cluster, put some gas on top of it, and let it run from a hydrogen to a redshift, and compare different methods how to solve these equations with each other, then you get, for example, here is shown the exponential of these clusters, and you get pretty different results. And that was already pointed out more than 10 years ago by Carlos Frank and various other people. So there's apparently some problem in how to solve these equations properly. And unfortunately, except for simple test problems, it's not really so easy to get a handle on to tell which result is correct here. So more recently, this week there was also a paper by Cecilia Spinapieco, Markus Waterpool, and also many other people who did a similar code comparison. This time not only making non-radiative calculations, but also turning on all kind of feedback effects. So, and then they asked again, they tried to simulate the same object and manipulate like halo with gas, so you would expect to form some lateral spiral. And then they looked at the gas and the stellar distribution, or at the end, at redshift 0. And these are just different codes here, and these are the results. And obviously, this all looks pretty different. Now there are two reasons for the difference. So one reason is that you can of course change your feedback description, so how you treat supernova feedback and other feedback mechanisms. Now this is captured, for example, in these G3 runs, which are all gadget runs. So these CS and all these other runs are just different feedback descriptions, and you can clearly see that this has a huge impact on the morphology of the galaxy. This changes a lot of results. Now another thing you can change, you can just keep the feedback exactly the same and the star formation description and cooling, but only change the numerical scheme. So this is shown here, which is a repo calculation, so for this new mesh code, versus for this old SPH code gadget, and this is really only changing the hydrocycle. And you can also see that this also makes a significant difference. So obviously both is important, and
What's R?
sorry, I think this is just around this.
Well, it's red.
Yeah. But maybe Volker can tell more about it, because I think the physics in that one was more or less the same as in the hypo one, right? It was this also primary cooling.
Yeah, I mean, there were 3 Atlantis runs in the study. One of them was essentially the same, essentially weak feedback and no feedback, no outflow. That is what the other one is the case. There, in particular, turns out that then the amount of stars formed in runs is exactly equal as the amount of gas that cooled down. It was quite interesting. Reassuring. So there's a substantial amount, I guess, get to this, but there's a particular difference in the way gas cooling works in these windows. In the 2 mesh codes in this study, the result was equal and was systematically different from the original. Yes, at some level we do. I will talk a bit about this tomorrow. So.
Yeah, okay, so the bottom line of this is I just want to point out that there are both uncertainties and the feedback description and in the numerical scheme, and a priori it's not clear which one is more important. Obviously both have strong effects, and obviously it's best to get both right, essentially. Now, along these lines, I just, in the last minutes, reported a bit on simulations that we did 3 or 4 months ago with February, actually, so these were simulations where we did exactly the same kind of initial conditions, both gadget and repo, and we had the same sub-resolution physics in both code, the same gravity solver. And the only difference between these calculations is really the hydro solver, which is in gadget the standard small particle hydrodynamics, and repo the moving mesh approach where Friday will talk a lot more about. And so we had some standard cosmology, and the physics that was implemented is very simple. So it's just really cooling or pragmatic mixture of helium and hydrogen. We had some kind of updated PV background, and we had some star formation and feedback description with an effective ASM description based on the Volker's model from 2003. So it's actually not important what kind of physics we put in, it's only important that both codes have exactly the same physics. So every difference you see on the next slides is purely due to the hydrosolver, so no feedback differences or so on. And these are just the different runs we did. So I will mainly show these high resolution runs, which are not very high resolution, but
so what's the epsilon is the smoothing?
Yes, that's the smoothing. Okay, so the first thing you can do, you can just make simple gas density projections. So this is shown here. So the full box was 20 megaparsecs, so this is the 20 megaparsec across here, and then I just focus here on one filament. And this is the gadget gas distribution and the repo gas distribution. Obviously on these scales, you do not see much of a difference, which is good, otherwise the bad on these scales will get very different results. But if you even go to the megaparsec scale, so if you look at the halo more in detail, like at the temperature structure and the density structure, which is shown here, and you can see that the repo temperature distributions are really significantly different from the gadget temperature distribution. And this is what Volker just mentioned. This is essentially some effect of the SPH calculation where some artificial heating going on, and I'm sure Volker will go more into the details of that process. And that effectively leads to the coded distribution in repo where this problem does not occur. And apparently also in the Comsys-Hum project that does not occur. Now if you go to even smaller scales, if you focus them on the galaxy that forms, then you get also in the morphology a pretty big significant difference, which is similar to the difference that I showed you before in the Villa paper when you compare the gaseous to the aqueous simulations. Now you can say that that system might be an exception, or that the Villa halo is kind of the exception, and maybe for another system the situation changes and looks better in SPH, for example. So, but that's unfortunately not the case. So these are selected galaxies at redshift 0 in these simulations, all taken from the moving mesh calculations for Repo. Now you can match these galaxies with the SPH galaxies, and then you get something like that. So you can see that there are some cases where you form kind of this. For example, in this case it looks not too bad in SPH. Also in this case it looks not too bad. But on average, like these systems, for example, the difference is pretty striking between the two calculations. And this is again only driven by the way how the audio equation is.
It's just a linear stretch.
Sorry?
A linear stretch.
No, this is a real thing.
So you really bring out the whole density stuff.
Yeah. Okay, and but you can also look at it more quantitatively, not in projections, but in measurements like the half mass radii. So this was something that Duchamp cherished it. So here's the function, the half mass radii as a function of halo mass. In red, it's shown the moving mesh calculation in SPH, in blue is the SPH result. And this is just a redshift 2 and this is a redshift 0. And you can see essentially the same effect we saw in the images before. Now you can also look at the specific angular momentum, again in red, in blue catch, and you can again see this is just different components, this is gas, stars, and total variance. And you always get this effect that the angular momentum is just larger, which makes kind of sense because of the larger disks. So I think I will stop here so and just give a brief conclusion on the three forms of matter that I talked about. So in the collisional case, I've mainly focused on dark matter, and there the interesting question is what is really the small scale structure of dark matter. And so previous models, especially analytic models, assume that you have a very low number of fine grained streams near the sun, so typically of the order of 100, which would imply that there's a significant impact on detection dependence. But that we could show now is not correct. Because there's a lot more mixing going on just because of the dimensionality of the problem and because of the small scale problems. Then there were also claims that you have dense caustic structures in the halo which could lead to strong annihilation radiation. This is also not the case, again, because of this mixing issue. The caustic density just decays a lot faster in these more general systems. Then based on these 2 points, it was sometimes stated that the annihilation radiation that we calculate with embodied simulations is missing a large fraction because all these small scale structures are not resolved. This is also not true because even in the outer part, the contribution of fine grained streams and caustics is below 10%. So all these 3 points, of course, change if you turn on the Sommerfeld enhancement, then you really get the fine grained distribution dominating the signal. But whether there is some Sommerfeld enhancement or not, that's not clear. But if it's the case, then I'm going to take this into account. Now, in the Sommerfeld enhanced models, I also mentioned that there's a self-interaction between dark matter. So now we have the case that we have both from the particle physics and from the astrophysical side the motivation for self-interaction dark matter. Particle physics from the Sommerfeld scenarios and astrophysics from these new massive dwarf areas, which kind of nicely work now together. So you have one model which puts all 2 problems in principle. And indeed it makes, although these are just preliminary results, indeed it makes the massive dwarfs less dense without violating any other astrophysical constraint. Whether this is a solution to the massive dwarf failure, I don't know, but I'm pretty sure it reduces the tension between the observation and simulation designs. And in the last part of my talk, I was talking about collisional matter, which is kind of the ultimate goal for predictions. I mean, when you compare to observations, you have to take this into account. But they are, unfortunately, compared to the embodied calculations of dark matter, they are pretty significant uncertainties involved. Even in the hydrosurface, not to mention the feedback where there's also a huge amount of physical uncertainties involved. And of course, in SPH, for example, you can overcome some of the shortcomings of the problems of SPH, like the small pieces that we solved, by invoking some sort of substrate physics. You just change your definition, density threshold, or your feedback description, can make the disks look more reasonable. Then the question is, of course, whether this is reasonable or not to do this based on the fact that your hydrosolver might suffer from severe effects like Fodder, which we will explain on Friday more in detail. And I think I will stop now.
Any question about when we're doing the collisionless or less collisions, dark matter and cores? You have the cores are actually getting out toward the kill first.
Yes, that's true. They reach the further to the power.
What would happen if you try to simulate a bigger galaxy? Somewhat collision or
A bigger galaxy, you mean a more massive?
more massive?
Then it will go, this effect will become, the core will become smaller because in these the velocity dispersion might go up, and then you have this. So for example, on the cluster scale, you have a very, very small cross section essentially because of the velocity dispersion.
So velocity drops off.
Yeah.
Less.
Yeah, that's now the nice thing about that cross section.
So that's how you hide this.
Yeah.
Because you want to see the.
Yes. So the nice thing is now you can really tune the velocity where you want the effect. So you can tune it to the dwarf.
Or ultimately, you can measure the cores in those objects and tell you what the.
Well, again, yes.
So, for exactly this problem, this failure is based on 6 halos. So, what do you think the probability is that we happen to be in a halo that doesn't look like one of these 6?
Yes, that's of course a possibility. But I think this is pretty unlikely because so Mike also did this Millennium 2 simulation, and these 6 halos were essentially chosen from the Millennium 2 simulation. Now, he looked at the Milky Way halos in this Millennium 2 simulation and compared their arrest properties in terms of very structural properties compared these to the 6 ones. And these 6 ones kind of cover or are not extreme and cover nicely the regime that is expected, the variance that is expected from based on the large scale simulation. So but there's always the possibility that that is the case, but I think it's pretty unlikely, and especially since he did not only look at the Aquarius halos, he also looked at the scalar K halos. I'm not sure whether he also looked at one of the G halos, but at least he looked at the Vela K, which even have very different cosmology. Their signature is significantly different. And there he found the same problem. So it seems to be a pretty robust problem.
In the last part of the talk, if you follow the gas streamline in, where do they deviate to set calculations? Are they overlapping until they reach, the disk, and then they deviate from there on, or do they deviate?
Well, that is something that mainly talked about that. So the point is that the amount of collision that we get in Hydro is significantly higher than Gadget. Now, the reason for that is that the deviation where the codes deviate happens already further out in the halo, and it happens already close to the cooling radius. So near the cooling radius, we have already a larger temperature of the SPH radiation compared to the other radiation. So that implies material that can cool down to the sun's supply is already very different, but the differences show up already at the cooling radius close to the radius. It's not largely different.
Yeah, you find there's a significant difference in the treatment of turbulence and the find that the dissipation quantum radius is quite different. So basically, SPH code needs a place where a lot of gas is actually supposed to cool, which is actually not too far away from the able to cool radius. And that gas that cools there is the best of the choice. That's why the supply already the cooling supply that comes is quite different. So it does not happen on this, it's actually very confusing.
You explain this more.
So, is it clear to extrapolate
point out that size scales is usually needed in understanding the concepts. So that's a big advantage. So that then I understand how small the scale is all the Collisionless simulation. Maybe you can extrapolate to very, very tiny scales.
Yes, well, so for the detector, for example, it's just important how many streams cross that region. So that's not really a spatial scale, it's just a number in velocity space, how many streams you can disentangle in velocity space. And the method essentially, yes, that will, the way it's constructed, resolve any number of streams. So that's very, for example, very different to the method that Tom Abel and Shandarin and others proposed a few weeks and months ago, where you are still kind of resolution limited. Because they do this calculation of the dark matter distribution and then try to recover the functional properties of the crystals. Now here we really dynamically attach local phase space volumes and track in time how this is deformed, and that can be done very well, and then you are essentially not limited.
Except for some noise, of course, the pi tensor is not perfectly calculated.
Yes, that's true. I mean, there's one issue that for these calculations to get since we need the second derivative of potential, we need to employ typically larger softening length for the calculations. But in the region outside of the softening length, it's in principle you can listen all the streams.
I have a question. You mentioned how there's a tie-in between Sommerfeld enhancement for self-annihilation cross-section and this kind of similar Sommerfeld enhancement type self-interaction.
Yeah.
How tightly do those two go together? And what I'm specifically asking is, do you expect this kind of self-interaction between low velocity particles to destroy your previous result that caustics become more important for self-annihilation and Sommerfeld enhancement? If you make enough Sommerfeld enhancement to get significant self-annihilation in a caustic, you also get enough self-interaction that the caustic is destroyed anyway.
So to the first part of the question, how tightly they are tied together, these two things. So when in 2008 these results came out of Formula, then various people, Tracy and Nima and others, proposed the kind of unified theory. In this unified theory was already something that the Sommerfeld enhancement put in, which was mediated by some method, as engaged by some new gauge boson, essentially could be vector or scalar. And but this effect would also then automatically lead to the side effect. So it was from that model on, it was already in. Now it's of course true that the calculation for the caustics I showed before did not take into account the second action. So I'm not 100% sure how these results will change. I mean, so I think the bottom line of the talk will still be correct because it says that that the streams will dominate in the Sommerfeld enhanced regime, whereas the caustics become virtual. I think that will still hold. But I'm just not sure whether the difference will be still as large as I showed, or whether there will be other effects between the second action. But again, I cannot answer this.
Any other questions? In that case, let's thank Mark again. We'll be taking Mark out to dinner tonight. Probably leaving here around 6